Number one, in plane strain approximation, 2D approximation, all components of a stress, strain, and displacement are independent of the out of plane axis Z. True or false? It's true, right? That's what we showed last time, or the time maybe 2 classes ago. That's easy. In plane strain, out of plane components of the strain, stress, and displacement are 0. No, why not? Yeah, sigma ZZ is not 0, right? So all I needed for you to write was that. No, I don't know why you were writing a lot of things. In both plane strain and plane stress, we can't have body force Fz, right? So if you have looked at the plane stress, the same thing happened there when you were writing the equilibrium equation in the Z direction. So this is true. How about plane stress? All stresses are independent of it. Let's go one by one. The stresses in plane stress. Do you have anything in the, are they all independent of Z?
Yes.
Yes, actually stresses are. How about the strains? Also, because you have Hooke's law. And displacement? No. So even in plane, what happened? Kingsley was giving Gerald advice to gamble, right? This didn't work here. So even in plane displacements, if you remember from the video, even in plane displacements are not independent of Z, right? So this is false. And all you needed to do just to say that, displacements are a function of Z. And in plane stress, how about the out of plane components of a strain, a stress, or displacement? Are they all 0? No, they aren't. So this is also false. And the last one, maybe the wording was not that great. Are they both mathematically clean problems?
No.
Plane strain is. Plane stress isn't, right? Okay, so this is what I wanted to go through before we start kind of a review of plane stress here. So now let's look at one other form of a stress. There are a few others, but this is the last one we look at, the generalized plane stress, which you may not have heard about before. What is going on here? Let's see. What is going on? Okay, I don't know. Let's close and start again. I need a new version. Some of you have much nicer. This looked good 4 years ago, but not anymore. So very, very quickly, let's look at another case which is discussed in your textbook, and that is generalized plane stress. So you saw that the plane stress formulation was not exact. When we were writing the equations, we would just ignore some of the equations because they could not be trivially satisfied. So mechanicians, they came up with a different or a new kind of form, a modified form of plane stress, which doesn't have this problem. And this is defined as follows. If you remember, the plane stress case is good approximation when you are dealing with a structure whose thickness is much smaller than the other dimensions. So if we look at a structure like that, and imagine that you have a mid-plane, so this with the dashed line is the mid-plane, so the cross-section which goes through the middle of the thickness, and we are having, this is actually, we are looking at a coordinate system which is going through a point in the mid-plane. So this is to my best ability to draw that. And you have a thickness of 2h, so h above the mid-plane and h below. So it is 2h. So this kind of stress is defined using the average field quantities. So if we have a quantity, for example, if we have a field phi, let's just consider field function of x, y, z. We can define phi bar as the average of the field through the thickness of this domain. So I guess you know from calculus that to take the average, you basically take the integral of the field and then you divide it by 1 over 2h, the thickness in this case. So this will be averaged field through thickness. Now, what happens here is that if we take this averaging, we are basically getting rid of dependence on z, right? So the phi bar is just a function of x and y. Using this kind of definition, this averaging, they came up with this generalized plane stress, which is defined as follows. So these are the conditions. Using the same notation as before, we assume that u, v, these are displacement in the x and y direction, fx, fy, these are even functions of z. So it's specular a little bit. So z is the direction through the thickness. We assume that u, v, fx, and fy are even, which is another way of saying that they are symmetric through the thickness, right? If they're even. At the same time, you assume that w and fz, they are odd functions of z. If we make this assumption, what would be W bar? What would be the average value of the out-of-plane displacement through the thickness? 0. If it's If it is an odd function, it would be 0. And how much would be the value of w on the mid-plane? If you have a function which is odd, it's 0, right? It has to be 0 also. Because z and negative c should be negative of each other. So at that point, this is also 0. And then the other condition is similar to what we had in plane stress. So you will have traction-free surfaces at z equal to plus minus h. So on the top and bottom surface, again, you will have traction free. And the averaged value of sigma zz would be also 0. So the averaged out of plane stress component, you want that also to be 0. So that's kind of the definition of this generalized plane stress. So why to go through this pain of defining so many assumptions? It turns out that if we make these assumptions, then all those equations that you could not satisfy for plane stress that we said, if you have watched the video, I said we forget about them as if they don't exist. So you just ignore that you are not satisfying. They all become satisfied. So it becomes mathematically rigorous, mathematically clean solution. And the equations, I'm not going to write the equations here, but they would look like the plane stress equations. Instead of having the fields, you have averaged fields. So just to give you an example, for example, if you look at the Beltrami-Mitchell equation, then it would look something like that. Before you had Laplacian sigma xx plus sigma yy equal to -1 plus nu fx comma x plus fy comma y. So now all these get a bar. So yes. Please. Move the projector down a little bit. Oh, sorry. So if you do that, then all the equations become satisfied, everything becomes clean. There is only one problem with this formulation. It doesn't really have many applications. There are not many situations of practical interest where you can actually satisfy these conditions. So it's something good for an academic curiosity, but it's not practically very useful. So I'm not going to write the equations. You can find it in the book. I think I wrote down. It's 7. It is in chapter 7, part 3. But we don't, since it doesn't have much practical significance, we don't look at it further. Okay. So now we want to start solving these equations. Before starting to solve, I want to give you some kind of a summary and then overview of the solution strategies, and then we start with one solution strategy. So you have seen this many times before, but I think it's important to kind of bring together everything that we have learned so far and put it in kind of to summarize everything once again. So we over and over, we looked at the elasticity field equations. I suspect that many of you can write it down without looking, right? Let's try to do that. So what we learned in this class so far, this is playing with me today. We looked at the elasticity. I really need a better version, right? So you guys start writing the equations. Elasticity field equations. Why is it doing that? Normally when the battery is low, so sad. No. That's no. So close. So what do you guys have written up? So we talked about a strain displacement, which I'm kind of sure that everyone can write without looking at the notes. And we looked at the compatibility equation, which I think by now even that should be easy to write, right? Then we looked at the equilibrium equations. And you may have seen that I graded homework number 4. There were a number of people who, when they expanded the equilibrium equation, they made mistakes. So when you have J, it's summing up. So just please try not to make mistakes. And then we had the Hooke's law, right? Which, again, I kind of guess that many of you can write, not looking at anywhere. And I can write if I'm not in front of the class. You can write it either way. Okay. And then we talked about boundary conditions, which the homework was due today, and there were many problems. And whether you would use traction or you would just specify displacement. And if you remember, we said that wherever we specify displacement, we cannot specify traction and vice versa. And then I told you that, well, we typically either solve for a stress or displacement. So we had a stress formulation where you basically combined all those 15 equations and you got which equation out of it? Do you remember which one? Beltrami-Mitchell, right? So I'm kind of summarizing the whole semester here. Which looked something like that. And then we had displacement formulation, where you write everything in terms of displacement. And we got what equation? Navier equation. Which looked something like and then we looked at the 2D approximations. The two useful ones for practical applications are plane strain and plane stress. And plane strain, how did we define it? We said U will be a function of x and y, v would be a function of x and y, but the out of plane displacement will be 0. And plane stress, we said sigma xx would be a function of x and y, sigma xy would be a function of x and y, sigma yy would be a function of x and y, and I ran out of a space, I just say others are 0. Sigma zz, sigma xz, sigma yz, those other components are 0. So if I wanted to summarize everything we did in this semester so far, half of the semester considering the snow and cold days, this is this one page, right? Now, how to solve these equations? It turns out that there are several ways to solve them. So one thing that you could think about, what would be the first thing that you think about? You have a number of partial differential equations. How do you want to solve them? What would be the most natural way to solve them? Exactly, to just integrate and start solving them, right? And this is called a direct solution. So now we want to think about what are the solution strategies. So, general solution strategies. One is the direct method. So in this method, you basically integrate the field equations or a stress displacement formulation, apply boundary conditions, and then you have your solution. What do you think goes wrong? This all looks very promising, very clean. It just becomes very difficult. Yeah, most of the time you cannot solve it. The math involved becomes so difficult that you have to give up. I actually had an example for you, but I think we won't have time to go through it. So a very, very simple example becomes complicated very, very easily. So I skipped the example, but believe me, even the simplest example can get very hard very fast. So these are mathematically can become very difficult, so typically are not very practical. So the other kind of a little bit, so this is something you are familiar with. Another kind of method that people use in elasticity is something which tends to look a little bit strange, and those are inverse methods. So I have a quick example about that, which I think it's important to look at them because you are going to see them later. And these are very strange. So you first find some stress fields, and then you make sure that they satisfy the equations. And once you have them, you start looking for a problem that can be solved with those solutions. That's why they are called inverse methods, and they are not as logical as the direct method that I told you. So the very simple example I solved for you, I can see in your eyes like, what? Yeah, so let's just consider one example. And you are going to say that a lot when you see the area stress function, because sometimes it looks like things come from nowhere, right? So for example, let me maybe write it. So basically this is finding a specific problem. You basically first have the solution, you look for the problem. Finding a specific problem when I say finding a specific problem, I mean geometry, boundary conditions, body forces, everything which defines the problem. That could be solved by a set of particular stress or displacement fields which have been found to satisfy the equilibrium equations. So all of those equations that they have to be satisfied. So for example, so some of the examples that actually you have seen so far have had this kind of a nature. If we consider this a stress field where sigma xx is equal to some constant times y, and all other stress components are 0. So sigma yy is 0, sigma zz is 0, sigma xy, sigma yz, sigma zx, they're all 0. So if we assume that body forces are zero, so assuming that body forces are zero, you can easily show that this stress field is going to satisfy all the equations. When I say field equations, you all know that I mean the elasticity field equations that I wrote one more time today. Right. Now, the question is, what problem can be solved with this stress field? So you are convinced that this stress field, because it's solving everything, it should be the solution to a problem. So now your problem is to find that problem. So that's why it is called inverse method. These are coming from experience, like how to find that problem you have to have the experience. It is like, I don't know if you had this feeling when you took your first differential equation class. It looks like other people know a lot more than you and you don't know, because all these solutions start popping up into your class and you always wonder, how did you know that? How they came up. I remember very well how I felt. I was like, I thought I was good in math. I had no idea. Like, I was freshman. I took it early because I was so excited, and it was like, wow, I have no idea. All these solutions, right? I don't know how many of you have had this feeling. Yeah, the differential equation class especially, because there is, like, you have no logic. You are asking yourself, sitting there, where these solutions are coming from. So it turns out that in elasticity, because it's a very mature and established field, people have solved these problems over hundreds of years, and there are these kinds of moments where you ask yourself, just be sure that everything is okay, there is no problem. It's just that, other people have had experience, and it comes through a lot of trials. So for example, in this particular case, so the way it works is that you take a domain and you try to look to see what these stresses, what do they mean, how do they look like. Of course, this is a very, very simple example, right? I took a domain, I take a domain, like a rectangular domain. I just want to basically use this example to show you the spirit of this kind of solution strategy. So I take a rectangular domain like that. So everything 0, like y equal to 0, z equal to 0, xy, zx. What does it mean for the top and bottom surface for this domain? Traction free. So what's happening on these two other sides? It's linearly changing with y, right? So you're going to have, something like that if y is positive, and then you are going to have something like this. So this kind of a stress distribution reminds you of what? Tensile? It's bending, right? So if you use Saint Bernard principle, this is like having a moment. So when I say you start with the stress and then you go to the problem, this is what I mean. So you put it there and then you try to look at your experience and see whether you can recognize a problem which can be solved with this stress solution. Very strange way, but very common in elasticity to do this kind of equation, this kind of solution. And then there is the semi-inverse solution method. And in semi-inverse, as you may guess, you have a little bit of that, and you have a little bit of assumptions. You come up with some stress or displacement field, a part of it, and the rest you use the field equations to derive, and you put everything together and try to find a solution without showing you any examples or anything like that. Now, what we want to do next is to attempt one method of analytical solution, and this is using power series method. And some of you may have heard about it, using area stress function. So this is the solution method that we start looking into, goes under analytical solutions. And so how many of you are familiar with area stress functions? A little, Kingsley, here, a little. Okay, so it's not that all of you know already about it. That's I need to know that. So there are different kinds of analytical solutions, and one of them is using area stress function. So let's see what this is about. And again, if you have a moment where you wonder, where these things are coming from, don't worry about it. Think about the first time you saw differential equation solutions, and just think about that. These things have been developed over many, many years. Because I remember I was depressed for a week. I was very young, and I just couldn't understand why there is something coming out of high school when everything makes sense, and all of a sudden there are solutions that there is no way I could have thought about, and I didn't realize what was going on. So, area stress function. Now, let's go back to our 2D formulation, and let's write down the equilibrium equations. Now, this should be very easy for everyone. So, into the let me write. I want to make it such that by the end of this semester, everyone can write all the equations by heart. So, if you want to write it in 2D, we only have x and y. So we have xx, comma x. This doesn't end here, right? Then we have xy, comma y, plus fx equal to 0. And we have, of course, the y component. So yx and xy is the same. I write it like that, but you all know that it's the same as xy. Now, suppose that if the body force is a conservative field, so what can we say about a conservative field? Yes, that's the concept. But exactly, the curl is also equal to 0. We can say that the force is related to the gradient of a potential function, right? This is something that I guess everyone has seen. So suppose that the body force is conservative. all the things you said are correct. And what we want to use here is the fact that, you know, it is equal to the gradient of a potential function we call V. So where V is the potential can call it energy of it, right? It's a scalar field. Now, if we substitute this above, we can kind of collect the terms, right? I just write it down, and then we can examine it together, and I hope you agree that we just can collect the derivative. So I'm just substituting these relations in equilibrium equations. Maybe I should write it. So here is 1 star asterisk 2. So substituting we have sigma xx, I'm collecting, and then plus sigma xy comma y equal to 0, and then we also have against the sigma xy term, nothing happens to it. The other term you can write sigma yy minus v, and then the whole thing comma y. So now comes the kind of the magical part. So far everything logical, right? Airy, whose this function that you are going to see in a moment carries his name, notice the following. So Airy noticed that if you take, is it again doing this? Every time I go to a new page, it doesn't like it. So suppose phi is a scalar field. So suppose there is a scalar field phi xy as a function of x and y, such that sigma xx is phi comma yy plus v, sigma yy is phi comma xx plus v, and sigma xy is minus phi comma xy. Suppose that you are able to find such a field which is related to a stress components through these relationships. You can show that if you define the stresses using these equations, all the equilibrium equations are going to be trivially satisfied. So we should write this down. All the equilibrium equations, all the field equations are going to be satisfied. I'm not going to show this, but it's kind of easy to show actually. So now, remember a stress formulation? What was the equation? Which equation was the Beltrami-Mitchell, right? Now, if we substitute the expressions for a stress into Beltrami-Mitchell equations, you are going to get an equation in terms of phi, right? So, see what happens. Someone called Airy came up with this idea that if you have a field equation, if you have a field phi, and if the relationship between the stress and this field are as you see there, all these stresses are going to satisfy all the field equations. And you can check that.
So to clarify, it's all the stress equilibrium and the compatibility, it will automatically
No, I'm sorry, all the equilibrium equations. And now we put it in compatibility, the Beltrami-Mitchell, to see what we have to satisfy in addition, right? So if you substitute these stresses into Beltrami-Mitchell, you are going to get the following equation. I warned you about the way that it comes kind of out of nowhere. So now I reviewed the Beltrami equation for you. It's all in terms of a stress. Now if you use these expressions for a stress in terms of phi, you are going to get an equation in terms of phi, correct? So substituting these expressions for the stresses, in Beltrami-Mitchell, equation. So you are going to get for plane strain, maybe I go to the next, hopefully it's not going to freeze. For plane strain, you are going to get equation which has this form. You remember Beltrami-Mitchell, you have Laplacian, right? Now, each stress is related to the second order derivative of phi. So 2 plus 2, 4. It becomes actually a very good looking equation with a lot of symmetry. So as stresses disappear, everything is now in terms of phi. And then on the other side we have the potential function. So the plane stress case looks exactly the same, except that now that's why I'm using this color. Instead of this coefficient, you have just 1 minus nu. So the form is exactly the same. I hope this is not confusing. Just instead of that coefficient, the negative stays. Instead of that fraction, you just have 1 minus nu. And the function phi, as you may have guessed, is the area stress function. Airy is the name of the guy who came up with this. So basically, since we know that the equilibrium equations are satisfied, the only equation that you have to worry about becomes this equation, basically. We know that if you have the phi, the equilibrium equations are already satisfied. So one way to write this a little bit compactly is to use a different symbol, which is kind of, remember Laplacian? Now, instead of 2, 4. And what do you have in parentheses in front of the? It's the Laplacian of V, right? So everything can be so this is plane strain. And this Laplacian squared kind of operator makes everything look very neat. So if we defined, if you want to define this Laplacian square, which has a name, it is basically if you compare to the previous formulation, this is how it is defined, and sometimes it's called the biharmonic operator. Now, if f is equal to 0, if we don't have any body forces, so we can ignore the right hand side, it will be 0, right? There will be no body forces. So in either case of plane stress and strain, the equation becomes very simple. It becomes just this. And this is called biharmonic equation. So it doesn't matter if it is plane stress or plane stress. So how can that be? What does it mean? I'm saying that if there is no body force, the equation becomes the same. But we defined plane strain and stress and they were very different. What does that mean if this equation is the same? Are the stresses would be the same? It will be different. If you solve this equation and it's the same for plane stress and strain, if you get phi, what can you get from phi? The stresses. So they should be the same pretty much, right? But then what would be different? Yeah, exactly. Not everything will be the same. So stresses would be the same. Strains would be, you just have to use the relationship between a stress and strain to get the strains. But then the relationships are different between a strain and displacement. So not everything is going to be the same. Also the equation is the same. We still have 2 minutes, so it's good. So then the question is, okay, now we learned about this mysterious function. How are we going to solve it? How are we solving it? Oh, assuming the solution. I couldn't hear you for some reason. No. It's yeah, we have to assume a solution, exactly. So what kinds of solutions we can assume? So the first one, and I kind of started saying this early on, that we start with a power series solution. So you start with assuming that phi has the form like AMN, let's say XM yn, and then you solve it, and then you go back and see what kind of problem can be represented by that solution. So it's very interesting, but also it can be a little bit unsettling if this is the first time you see it. But don't worry about it. Just think about differential equation, how strange it was in the beginning and how it is now. It just comes now when you see some forms of differential equations, you all know what would be the solution, right? Because that's your experience. But a college freshman, it's very, when you see it, I never forget that feeling. Okay, so question, Kingsley? Just a stretching. Okay, great. I think this is a good place to stop because I don't want to start something.